Ask any AI. What happens when you drop a glass off a table? It'll say, the glass falls and shatters on the floor. Correct answer. But here's what's actually happening inside the model. It read your words, turned them into tokens, and predicted the most statistically likely next token. Over and over, one token at a time. That's it. There's no glass inside the model, no table, no floor, no gravity pulling anything downward. Just probabilities over text. And this isn't just one model. ChatGPT, Claude, Gemini, Llama, DeepSeek, every major AI you've ever used works this way. Next token prediction. They're extraordinary at language. They can write essays, debug code, pass bar exams, but none of them have any idea what the physical world actually looks like. So what would it actually take for an AI to understand the world? Not to describe it in words, to actually understand it. One approach is to make the model predict everything, every pixel of the next video frame, every detail of what comes next. But think about how insane that is. You're watching a cup of coffee sitting on a desk. To predict the next frame, you'd need to predict the exact color of every single pixel, the reflection in the coffee, the shadow under the cup, a speck of dust on the desk. Millions of pixels, most of them completely irrelevant to what's actually happening. A toddler doesn't do this. When a toddler watches you throw a ball, they don't process every photon hitting their eyes. Their brain builds a simple model. Ball goes up, ball comes down, arc, gravity, trajectory. They strip away everything that doesn't matter and keep the essential structure. That's not prediction, that's understanding. In 2022, Yann LeCun proposed an architecture that works more like that toddler. Instead of predicting raw pixels or tokens, it predicts simplified representations. Think of it like this. You see a photo of a dog in a park. An encoder compresses that image, not into pixels, into a sketch, the shape of the dog, the layout of the grass, the spatial relationship between the dog and the trees. All the irrelevant stuff, the exact shade of green, the cloud pattern, a leaf on the ground, gone. What's left is the essential structure of the scene. He called it JEPA, Joint Embedding Predictive Architecture. And the key idea is this. Take an image and hide part of it. Block out a region. Now, instead of asking the model to reconstruct every pixel of that hidden region, ask it to predict the simplified representation. Not what it looks like, what it means. If you hide the right side of the dog in a park, the model doesn't need to guess the exact fur pattern. It just needs to predict there's more dog over there, and the grass continues. This changes everything about how the model learns. It doesn't waste capacity memorizing pixel-level details. It learns structure, relationships, what matters in a scene, and it does this without any human labels. No one tells the model this is a dog or this is grass. It learns by predicting the hidden structure from the visible context, entirely on its own. Self-supervised. But there's a trap. If you just train two encoders to predict each other's output, they'll cheat. Both encoders learn to output the same constant value for every input. Doesn't matter what the image is, dog, car, beach, same output. The loss goes to zero, and the model has learned absolutely nothing. This is called collapse, and it kills most self-supervised methods. JEPA solves this with a clever trick. The target encoder, the one processing the hidden part, doesn't learn through normal training. Instead, its weights are a slow-moving average of the context encoder. Think of it as a shadow. The context encoder updates quickly with every batch of data. The target encoder copies those weights, but slowly, with a delay. The context leads, the target follows. And because the target can't just snap to match the context, neither of them can collapse to a constant. The lag forces them to learn real structure. So JEPA works on images. You mask patches, predict their structure. That's called I-JEPA. But then Meta's team asked a much bigger question. What if you don't mask patches of an image? What if you mask frames of a video? This is V-JEPA. Video JEPA. And it learns something remarkable. By predicting the hidden frames, the model starts to understand motion. A ball going up will come back down. A person walking will keep moving forward. An object that goes behind a wall still exists on the other side. Object permanence, trajectory, cause and effect. all learned from just watching video. No labels. No one told the model about gravity or momentum. It figured it out. And this is where it gets powerful. If a model can predict what happens next in a scene, it can plan. Imagine a robot arm reaching for a coffee cup. Before it moves, the world model simulates the outcome. Approach from a steep angle. The cup tips over. Hot coffee everywhere. Try a different grip, come in from the side. The cup lifts cleanly. The model runs these simulations internally, picks the best outcome, and only then does the robot actually move. It's thinking before acting. That's a world model, not an AI that describes the world in words, an AI that has an internal simulation of how the world works. It understands that gravity pulls things down, that cups can tip, that coffee is a liquid that spills. Not because someone wrote those rules, because it learned them. From watching over 1 million hours of video the same way a child learns by watching the world around them. Yann LeCun is one of 3 people who won the Turing Award for inventing deep learning. He co-created convolutional neural networks, the architecture behind computer vision. He was the chief AI scientist at Meta for a decade, and in late 2025, he left to start AMI Labs, Advanced Machine Intelligence. He raised $1.03 billion in a single seed round, one of the largest AI seed rounds in history. And his thesis is simple. Large language models are a dead end. His argument goes like this. Large language models are trained on text, but text is a tiny fraction of human knowledge. Most of what we know about the world we learn by seeing it, touching it, hearing it, moving through it. A child learns more about physics in one afternoon at a playground than an LLM learns from the entire internet, because the child has a world model and the LLM does not. So what is AME Labs actually training on? Not text, but the real world. Video, audio, LiDAR point clouds, robot sensor data, the kind of data that captures the physical world, not just language about it. The idea is to build models that learn the structure of reality the way a child does, through observation and interaction. And they're targeting the applications where understanding the real world actually matters. Robotics, healthcare, industrial automation, autonomous vehicles, not chatbots, not essay writing, the physical world. So is LeCun right? Are large language models a dead end? Honestly, nobody knows yet. Large language models are getting better every month. They can reason, they can use tools, they can write code that works. But there's a question underneath all of that progress that nobody has answered. When an AI writes a perfect description of a glass falling off a table, does it understand what it just said? Or is it the most convincing autocomplete ever built? That's the question LeCun is betting $1 billion on. And whatever the answer turns out to be, it's the right question to ask.